Okay, so let's today look at. So this is chapter 6 in your book, the Nelson book. We are going to look at two things really. One is we're going to look at Kepler's 3 laws, and then we're gonna tie it in or talk about gravitational fields. Okay, so the first one is a study of how planets move around the sun. And Johannes Kepler studied the motion of planets and came up with 3 laws that are written here. So do you have this document?
Yeah, you posted it on Schoology, like
Okay,
from
okay.
before, I guess.
Okay. So his 3 observations were that when planets go around the sun, the orbit's not circular; they're elliptical. Trivia question: who actually came up with the idea that the planets go around the sun? Give you a hint: Polish astronomer Nicholas Copernicus. Does that name ring a bell?
Yeah.
So
Nope.
No, that's okay. Because before that, people thought that the Earth was the center, right, of the solar system. Anyways, but Copernicus had that correct, but he thought the orbits were circular. So that differs a little bit into as to what Kepler thought. The second law is that, and it has to do with something called angular momentum, okay? Which says basically that if you look at, for example, let's say equal interval of time, okay? So let's say if you look at this diagram, you have the Earth going around the sun, and we were to measure the area that it sweeps out, which is in purple here, for a month. Let's say when it's farther from the sun versus when it's closer to the sun, okay? Now, the amount of area swept out is equal. Now, why that happens is because the closer the Earth is to the sun, the faster it moves. And the farther it is, the slower it moves. And the reason for that is we actually talked a little bit about this idea. This is a function of 2 things. So angular, because we talked about momentum, and in chapter 3 we talked about circular motion, right? So angular momentum is basically a function of 2 things. One is it's a function of its rotational speed, but it's also a function of the distance that the mass is from the center. So what this means then is, if I look at this picture, if the Earth is closer, so if the distance decreases, that must mean that the rotational speed around the sun must increase. The reverse is true. If the Earth is farther, so if I look at when it's over here, that distance is farther. So if the distance goes up, that means the rotational speed goes down. If you recall, we talked about, I think, was it a neutron star? I believe we did discuss the rotational speed of a neutron star, right, a while ago. And if you remember, the rotational speed of a neutron star was like some ridiculous value. And that's because when a star collapses, so a star rotates slowly, like our sun is rotating, I can't remember how long, it's like once every so many days, I think. But as it collapses, as the distance decreases, its rotational speed must increase to preserve that angular momentum. It's no different than the figure skater. If you ever seen a figure skater, when they're spinning and they pull their hands in, they rotate at a faster rate. Okay, so Copernicus, because he thought the orbits were circular, thought also that the speeds did not change. So that's also a difference, okay? But what I want to actually focus on is on his third law, which actually comes from chapter 3. Is it chapter 3? I think it was chapter 3. Which has to do with, if you recall, chapter 3, we looked at centrifugal force. And we came up with an equation that we could use the period. When we set the centrifugal force equal to the universal law of gravitation, you can get an equation for the period. And if you set them equal to each other, you get an equation that looks like this, where the period squared is equal to 4 pi squared times r cubed over g times the mass of the central body. If you don't remember that, you can go back to your notes on centrifugal force. But the interesting thing is when we look at this, if I look at that equation, right? There are, in this equation, if I think about like an object rotating around the sun, there are 4 constants in that equation. Okay? If it's any object like the Earth or Mars or Mercury or Jupiter going around the sun, then the 4 constants would be the number 4. And by that, that's because it's number, if you recall, we're substituting V has 2 pi r. So when you square it, you get your you get 4 and you get pi squared, right? That's why we have 4 and we have pi squared in this equation. So those are constants, and then g is a constant, and the mass of the central body is a constant. So really the only thing that changes when we're looking at the planets going around the sun are the orbital period and the orbital radius. And it shows that the orbital period is when it's, if you look at it, it's t squared equals these constants r cubed. So what you can do then is you could set up a relationship. We could set up a relationship because these things here, these are all constants. So I can put r cubed and set up a relationship of period to radius, and basically say this. I can say that if I know the orbital period and orbital radius of any planet, as long as I know, let's say, for example, for Earth, okay? I have the orbital period and the orbital radius of Earth, okay? Let's say we think of it as a circle. I know it's not a circle. Let's think of it as a circle. Let's say the radius is 1 astronomical unit, okay? So let me actually just take a screenshot of this so we can zoom in. I should write, okay? Okay, let me just make this big. So if I move r cubed here, I have a relationship of period of a planet squared over its radius cubed for any planet, right? So what that allows me then to do is to think about being able to determine like something about another planet. Like say, for example, in the question we're going to do about Jupiter, right? So if I have Jupiter's distance, I should be able to predict its period, because as long as I know like Earth's period and Earth's distance, I can predict Jupiter's orbital period. So for Earth, and by the way, as long as the units are the same, it doesn't matter. So the period could be in days. The distance could also be in kilometers. But then if you did it in days, you would have a much bigger number to work with. And if you did it in kilometers, you would have a much bigger number to work with. So Why work with big numbers when you can work with small numbers and get the same answer? So let's do this. Let's get this answer in years, and let's get the distance in AUs if we need to get the distance. But in this case, we don't. We're just looking for the period. Okay. So Kepler's third law says that we can figure out the orbital period of Jupiter. So I'm going to call Jupiter T1 because, or its orbital period T1 because that's on top. So I'm going to say T1 is the orbital period of Jupiter. T2 will be the orbital period of Earth. Okay. R1 is the orbital distance of Jupiter. That's for Jupiter. And then R2 is going to be the orbital period of Earth. So I'm going to make 1 Jupiter and I'm going to make 2 Earth. Okay. So we're going to solve for T1 squared. So T1 squared is going to equal R1 over R2 cubed times T2 squared. Okay, I have to separate these two out. So that actually should be, so when I was trying to do this, so this is supposed to be like a bracket around all of this. I couldn't do it on Microsoft Word, so that's supposed to be a bracket around everything. Or you could just write it as T1 squared over T2 squared equals R1 cubed over R2 cubed. Okay. So the orbital period of Jupiter squared, so that means we can get rid of that and solve for the orbital period of Jupiter. Okay, so let's take a look at that. That would be the square root. Let me actually put it over here. Of R1 over R2 cubed. So R1 is the orbital distance of Jupiter, because we define 1 as Jupiter, 5.2, over the orbital distance of Earth, which is 1. That's good. That's that cubed times the orbital period of Earth squared. Okay, so what does that give you as an orbital period for Jupiter?
$11.8.
11.8?
Yeah.
Very good. Now, what's interesting is we can apply this to any planet, right? Again, you have to just know you have to compare it to a planet that's known, right? You know, the reverse is true. If we know its orbital period, we can predict its orbital radius. So what's really cool then is if actually you take Kepler's third law and you actually apply it to the actual distance in orbital, like the actual distance in whether it's AUs or kilometers or the orbital period, these are the actual values. This is the graph, okay? And if you plot in the values, Kepler's third law to where they actually are, it's almost like an exact complete match. Like that third law is extremely precise. It works very, very well in being able to predict distance and periods of other planets. So bravo, Kepler. Good job. Any questions about the 3 laws? So you can see here the actual planets on this graph. Okay, this graph being a function of on the y-axis is this is the period. So that would be x cubed, y equals x cubed, and then the radius would be this distance squared. Okay. Okay, so let's then move on to what I think is a really fascinating topic, which is gravitational fields. Really, really cool topic. Okay. So here's a question I want you to think about. What do you think is meant by the term? Because it's got the word field in it. So what do you think is meant by the term gravitational field? Like when you think of a field, right? What do you think of? What fields come to mind?
It's like the area that a mass that a mass's gravity influences.
Very, very good. And here's an interesting thing. So yeah, like a soccer field has an area, a football field has an area. Yeah, it's the area of which we experience that whatever in this case be gravity, right? Now, what's really interesting is we've been using the equation for the universal law of gravitation, right? But I want to show you something that it's one of those things where if you like you just take it for granted, you don't really think about it. You realize there's a flaw in some of the logic. So I remember a while ago I was talking about I was listening to a podcast, it was a Joe Rogan podcast. He was talking about why is it that you never see bullets unless they're in slow motion. You never see bullets, right? In a movie. You always hear them, but you never see them. But you always see the laser. Which is weird, right? Because the laser is traveling like maybe I think it's 100,000 times. No, I think it's like 1,000,000 times faster than the bullet would travel. Maybe not quite 1,000,000, but close to 1,000,000. So, and I was like, yeah, it makes sense. I never think of that, but yeah, why do you see a laser? So, do you remember we talked about the universal law of gravitation is written as this, right? G m1 m2 over r squared. Now, this allows you to predict the basically the force of attraction between any two objects, right, that have mass. But here's the question. Do you guys, have you studied or know anything about black holes? Why is a black hole black?
Because no light can escape from it.
Yeah.
It's not black. Yeah.
Well, inside the black hole is black, right?
Yes. I
The
haven't
outside,
seen it.
yeah, the outside is not black, but the inside of the black hole is black, right? So if you were in a black hole, if I was in a black hole and I was to shine a flashlight, if I was trying to get a beam of light to you, let's say I'm in the black hole. So let's say, okay, this is me. I'm in here, okay? And I'm trying to shine a beam of light to you. Would you ever see it? You wouldn't see it, right? Now, here's something that's interesting. Here's a simple question. What is the mass of light? What is the mass of light? Anyone know?
Is it 0? Does it have any mass?
No. Yeah, you're right. It's zero. It's zero. So if we put 0 in this equation, then how is it that light is affected by massive objects? Because it is. Now, obviously, there's a limitation to this equation, right? There's something that's missing, and that has to do with the explanation of what gravity actually is. This equation allows us to calculate the force of attraction, but it's a limited understanding. Who came up with this equation?
Newton.
Yeah, very good, Newton. But remember, one of his critics, or one of the criticisms was he didn't explain how gravity worked. Along comes Einstein and says, well, gravity, what it is just really a bending of space and time. Now, if we think of it that way, then it kind of makes sense as to why light would be affected by gravity. Because if you have an object sitting in space, so imagine that here in this image here, this is my gravitational field of Earth, okay? So the area of which Earth exerts gravity. Now, sitting on this field is the Earth, and you can see it causes an indent. Now, why would light be affected by a massive gravitational object? Is because the object sits in space and it causes space to bend, and because light follows straight lines, and as the light travels, what happens? It's just going to follow the bend. Change the color on that. It's just going to really just like a marble follow the bend. So the reason why light bends is not because, it's not because if we put it in the equation, force of attraction is 0. It's because it's just following the curve created by the object sitting in space. And you can see that here. So imagine that we have a massive object, like a supermassive black hole sitting in the middle of this image, okay? And you have behind it, let me just close some of these windows. Behind it sits some galaxy, okay? Or maybe a bunch of galaxies. Now, what happens is because the black hole creates a bend in space and in time, by the way, what happens when the light comes from these objects behind the black hole, it just simply follows the curved path created by the bend in space by the black hole, right? Now, what that does then is it actually gives you the illusion that you have multiple images of these things behind the black hole. And the reason for that is because it's really no different than, remember in grade 10, you guys did optics? And when you look at an object in water, you know how light bends? So let's say there's an object in water and the light bends like this. And when it bends, you perceive the object to be somewhere else. Now, this is, if you remember, this is a refraction, right? Now, why do you perceive the object to be somewhere else? It's because you see in straight lines. So when this light is coming from behind the black hole and it's basically being bent by the black hole because it's creating an indent in the gravitational field. You see things in straight lines. So for you, you would see things over here and you would see things over here, and we give you like multiple images of this thing behind the black hole. This was actually proof that Einstein was right. This concept that you're seeing here is actually called gravitational lensing. Because if I look at the way the light is going around, doesn't it kind of look like a magnifying lens? If you look at it, the magnifying lens has like this kind of a shape. It has a very, very similar shape, right? So this is kind of cool. I mean, this is proof. When astronomers saw this, like, oh, wait a minute, we're seeing multiple images of these things. What's going on? And then they realized, oh, because light is just being bent by some object, and this is gravitational lensing that we're seeing, which is really, 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 really cool. Okay, so
can I show something?
Sure. Can
you
jump in?
Yeah, I think you showed this. Oh, I don't know. Wait a second. I think you showed this.
Do I have to stop sharing?
Yeah, you have disabled attendee screen sharing, so I can't share mine.
What do I have to do?
Oh, wait a second. You have to enable us to like share our screen.
Oh boy, how do I do that?
It's the picture that you showed that it had like multiple images of a galaxy. It was like an actual picture.
Do you have that image?
Yes. Yeah, I do.
Yeah. Why don't you post it, and I can share it with the students? Yeah, it was a grade 9 activity where we were trying to figure out like it was just a really cool image of where an actual example of this gravitational lensing. Yeah, can you post that for me?
Yeah.
Thank you
sure.
so much.
No problem.
So here's a black hole, right? When a black hole is an extreme indent in the gravitational field. Basically, if anything goes in, what's called past that event horizon, it ain't coming back. We're going to come back to this because I want to show you something really cool. Because we can actually calculate certain sizes that things would need to get down to become a black hole. Okay, but before we get to that point, I want to go back to the universal law of gravitation. Okay, because what we're going to do is we're going to talk about gravitational energy. Now, I know in grade 11 we talked about work as basically a change in energy, right? And we talked about, for instance, gravitational potential energy, where work is a function of mg times the change in height. Okay. Now, and we also last year talked about the universal law of gravitation. Okay, so if you recall, we said last year that work is also defined as a force times distance when these two things are parallel, right? Now, if I look at this example here, I guess my question would be, what does the area of that graph represent? The area being a shape. So here's force, and here's distance, and we know work is force times distance. So this area that you're seeing here should represent the what? Starts with an E. Oh, I got a chat here. I can't see the chat. And I can't see the chat. Why isn't it showing up? Okay. The area represents the energy. Okay. Now, if you remember this is the pattern you would get if you were to use a spring, right? So in this case, it would be a triangle because as you stretch it, you have to exert more force on the spring to make it stretch even more, right? But the idea is the area under that would represent the energy. And we can calculate these two shapes because one's a rectangle, this one's a rectangle, and that one's a triangle. It's easy. Here's my question. How do we get the area then under something where it's not a rectangle or a triangle? Because if I was to graph F versus D using the universal law of gravitation, I would get a curve that would eventually approach zero. If R got big enough, then FG would basically approach what? Zero, right? So how would I get the area under that graph?
Oh,
I know some of you know. I know some of you know the answer to this.
Sure.
Yeah.
Okay. Should I? Not?
Yeah, say it.
I think, like mathematically, they take the antiderivative.
Very good. So if I take the antiderivative of this equation, I get this right here. That's the antiderivative of g m1 m2 over r squared. Okay. Don't worry if you don't know that. It's okay. You can just trust us on this. Okay. Now, what we can do is we can use this then, because this represents the area under that curve. We can use this as a way to actually measure the energy or change in energy using the universal law of gravitation, and actually compare it to the equation we used last year, because the equation we used last year for work is mg delta h. It works okay for small distances, right? But if the distances become too big, the problem is that equation doesn't work so well. And that's because little g changes, right? As you get further and further from the surface of the Earth. So what we're going to do is we are going to use this equation to figure out, because this is the change in energy. So because we can say it's no different than we talked about before, mg delta h, where h is what? h2 minus h1. We can set up a similar equation here so we can use that as a way to compare using this method versus this method. So let's look at an example of a question, okay? Let's imagine we're looking at a rocket that has a mass of 100,000 kilograms, and it's leaving the surface of the Earth. And we want to know the change in gravitational energy at a height of 1,000 kilometers, okay? So, you know, if we did this question last year, we would have done something like this. Oops, sorry. Let me make this bigger. Okay, so last year we would have said, okay, well, the change in energy of the rocket is the mass of the rocket, 100,000 kilograms, times g, times the change in height. So the change in height will be h2 minus h1. Well, h1 is the surface of the Earth. So we're going to say the surface is 0, okay? So 1,000 kilometers is actually going to be 1 million meters, right? So I'm going to convert this to meters. So h2 is 1,000,000, and h1 is 0. So in this case, the amount of work done is going to be 9.8 times 10 to the 11 joules. And it's positive because we're doing work against gravity, okay? Now, if we use this equation, which again comes from taking the antiderivative of the universal law of gravitation, we're going to get a different answer. It'll be close, but it's not going to be exactly the same. So let's take a look. So the change in energy between, so this would be like, you know, here's your curve. We're going to try to take the change in energy between 2 points, right? That's what we're going to try to do. Figure out the area between those 2 points in the curve. So R2 is 1,000 kilometers, but it's not 1,000 kilometers. It's actually 1,000 kilometers plus the distance to the center of the Earth. Here's the big difference between these two concepts. One is we need to consider this relative to the center. Okay, so when we set it up, the change in energy is going to be negative the universal law of gravitation, so 6.67 times 10 to the negative 11, okay, times the mass of the rocket, which is 100,000, okay, times, I guess I should go in order of what I wrote here. Let me go in order of what I wrote, okay? So big M is going to be the mass of the planet, which is, I'm going to just round it off to 6 times 10 to the 24, okay, times the mass of the rocket, which is 100,000. So I'm just going to change it to scientific notation, 1 times 10 to the 5. Okay, over R2. Now, R2 is the distance to the center. So here's the Earth. The rocket is about there. So that distance is the radius of the Earth plus 1,000 kilometers. So if the radius of the Earth is 6.3 times 10 to the 3 kilometers, then the rocket would be 7.3 times 10 to the 3 kilometers from the center, okay? And then obviously we want this in meters, so it's going to be 7.3 times 10 to the 6 meters, okay? Now, it's going to be that minus, so that's going to be that plus the second value, which is when it was at the surface of the Earth. So R1 being the surface of the Earth, okay? So it's going to be 6.67 times 10 to the minus 11 times the mass of the Earth times the mass of the rocket over R1, R1 being when it's at the surface of the Earth. Okay, so when we do this, we set it up like this, we get a different answer of about 8.7 times 10 to the 11 joules. So you'll notice that, I mean, it's depending on your perspective, but it's about, 90% close to the other answer. I guess if you can think of it that way. So it's pretty close, but it's still off by about 1.1 times 10 to the 11 joules. So it's off by quite a bit. So for objects that are being shot off the surface of the Earth, you don't want to be using this equation. You want to be using this equation to determine the change in energy. Questions? More questions? Okay. Now, what's really cool is we can actually now, because we define that the energy is the antiderivative of the universal law of gravitation, and we can use that to figure out the change in energy, which is what we did right here. We can do something really, really cool now. We can answer two really cool questions. One is, how fast do you need to travel to get off the surface of like a planet or a moon, for instance? And then you can use that concept to figure out an even more interesting question, which is how big or how small would something need to get to become a black hole? Okay. So let's tie in what we just did before with the next topic, which is escape velocity. Now, the idea behind escape velocity is, let me just open this up. Let me close some of these windows. Okay. The idea behind, well, sorry. Okay. The idea behind escape velocity is that, let's say you're on, in this case, the moon, and you shoot a projectile, okay, off the moon. Now, what speed would it need to have so that by the time it's so let me put it this way. Imagine that we just, so a rocket might not be the best example because when a rocket's taken off, it has a thrust. But imagine it was more like a bullet. Okay, we shot a bullet off the moon. Now, you know when you throw something in the air, it slows down because gravity pulls it down. But if you were to throw something fast enough, what would happen is it would be able to escape the gravitational field of the object that is trying to escape. So in this case, the moon, right? So what happens is you shoot something off the moon, like a bullet, okay? We know the bullet is going to slow down. So we know what's going to happen is its kinetic energy is going to slow down, right? It's not slow down. It's going to decrease. It's not, because its velocity is going to decrease. Okay. Now, what's also happening though is that as it's getting further and further away, we know that the gravitational field or the gravitational pull of the moon on the bullet will decrease too. Or the effects of gravity will decrease, right? So the minimum speed required to escape an object will be the point where the bullet gets to a particular location in space where the kinetic energy basically approaches zero, and there is no more gravitational pull from the object. So we can therefore say that the force of gravity is zero, but also the energy due to gravity is also zero too. So it's a point where the bullet gets shot off the moon, in this case, gravity is pulling it and trying to slow it down. The bullet is moving away from the moon, right? So maybe it's over here. So at this point, it's slower, but the gravitational field is also, the gravitational effects are weaker. And then it gets to a point where it actually comes to a stop, where it basically has no more kinetic energy, but there's also no more gravitational potential energy either, because it's beyond that gravitational field. Okay, so what we can say then is at that point it has no more energy, so the energy is 0. So I can look at an equation which says basically at any point the total energy of my bullet or whatever I'm shooting is the sum of the kinetic energy and the gravitational potential energy, right? Now, we know as the bullet moves away, they both decrease. And at some point, they'll both get to 0. So that means your total energy ends up being 0, okay? Which means then we can set an equation that says that EK, kinetic energy, is equal to the negative gravitational potential energy. And if you remember, the gravitational potential energy is the antiderivative of gm1 m2 over r squared. So that's negative gm1 m2 over r. That's the antiderivative of the universal law of gravitation. So what we can do then is we can say that EK is equal to gm1 m2 over r. And we could figure out the escape velocity for, let's say, a rocket. A rocket, again, being a bad example because, well, not really a bad example, but any object that's trying to leave the moon would have to have a minimum velocity of this, which is what we're going to figure out right now, okay? So we know EK is 1/2 mv squared, and that's going to equal big G m. So we'll call m1 the mass of the planet or the moon, whatever, and the other m, little m, is going to be the mass of the object trying to escape. So let's say we call that m2, and we call this one m2, okay? Over r. So obviously that means that we can cancel out the mass of the rocket or the bullet. Then what we could do is we could say that v squared would be 2 times big G, the mass of the planet. I'm going to put MP, but it's the mass of anything that you're trying to escape from, okay? Could be MS, star, moon, whatever, over R, okay? So that V then would be the square root of 2G MP over R. Okay, so in this case, the escape velocity of the rocket would be the square root of 2 times big G times the mass of the, well, it's not a planet, it's the moon. So the mass of the moon is, I remember looking that up. It's 7.4 times 10 to the 22 over the radius of the moon. We have to assume that the rocket is starting off at the surface of the moon. So that would be the distance to the center is simply just going to be the radius. And the radius of the moon is 1.7 times 10 to the 6 meters. So that would give me an escape velocity of about 2.41 times 10 to the 3 meters per second. And if you look up the escape velocity, because you can Google escape velocity for like the Earth, like the Moon, Jupiter, you would see that it's very close to that answer. I think it's like 2.39 because I did a little bit of rounding here. Questions about the connection between gravitational potential and escape velocity? Making sense? If you have any questions, just feel free to jump in. Now, what we can then do, one last step, is we could then take this concept and do something really interesting with it and figure out something like this.
Yeah, I have a question.
Yeah.
Is escape velocity like the minimum speed to escape
Yes.
thing. So if you go any higher than that, would you have energy at the end, or?
Yeah, very good. Yeah, so if you were, I got rid of my screen. So the minimum escape velocity is where you get to a point in space where your kinetic energy and gravitational energy is 0, right?
Yeah.
So if it was more than that, then you would have still some kinetic energy. Yeah.
Okay.
Yeah,
Cool.
very good question.
Thanks. Okay, thank you.
What's really cool is then we can connect this concept to figuring out how big you can, or sorry, how small you can make something so that it essentially becomes a black hole. We could use it to calculate something called the Schwarzschild radius, which is basically the maximum size something could be for it to become a black hole. It could be that or smaller. So for instance, if we took the Earth and we squashed it down to some ridiculously small size, we can make it into a black hole so that light wouldn't be able to escape from it. And the way you would do that is you would actually just simply think about the previous question that we just did, right? In the previous question that we did, we took the escape velocity, and we figured out that the escape velocity is a function. We said v, what's going on here? It's in the hand. Okay. We said v, well, what's going on? Just hold on. V is the square root of 2 times big G times the mass of the object that you were trying to leave. So I use a P, but you don't have to use P, over R, right? Now, the Schwarzschild radius is you're looking for R. So I'm going to go back and I'm going to do this. I'm going to say V squared is simply 2G m planet over R. And what I'm going to do is I'm going to rearrange and say R equals 2G m planet over V squared. Now, what am I going to use for V? Well, what I'm actually going to use for V is I'm actually going to substitute and say that V is C. Because for something to be considered a black hole, that means not even light can escape it. Right? If it's in a black hole, light can't escape. So I could use V, I can substitute V for C. And I can figure out that Schwarzschild radius by using, instead of V squared, I'm going to use C squared. Okay, so now what I can do.
Wait, I have a question again.
Yeah.
Sorry, what does C represent?
So C is the speed of light.
Oh, okay.
Okay. And
Okay.
remember, if something's a black hole, that means not even light can escape it. If it's in the black hole. A
Yeah.
black hole does emit radiation, but if it's in a black hole, light's not coming out. So we could use, instead of using V, we can use C to represent the maximum speed possible, which is the speed of light.
Okay.
So now if we put in our values, so 2 times 6.67 times 10 to the negative 11 times the mass of the Earth, Earth being about 6 times 10 to the 24, over the speed of light squared, which is 3 times 10 to the 8 squared. We get an answer of about 0.0089 meters, which is 8.9 millimeters or 0.89 centimeters. Basically, it's like the size of a blueberry. If we could squish the Earth down to something that has a radius of about 0.9 centimeters, so about 1.8 centimeters across diameter, then it would become that, or smaller, it would become a black hole. everything on this planet shrunk down to the size of a blueberry, it would become a black hole. We can do the exact same logic. Like, and if you Google it, like if you say, if I go and I Google, for example, Schwarzschild radius of Earth. Whoa, what happened there? Sorry. Okay, it actually comes up. I guess I figured out I didn't know how to spell. And you can see it's about 9 millimeters, right? What's interesting is it says that the sun, the Schwarzschild radius is about 3 kilometers. So if we did the same thing for the sun, we use the exact same formula. So we said 2 times g. Now the mass of the sun is about 2 times 10 to the 30 kilograms. And we divided it by the radius of the sun. Divided by c squared. Okay. If we do that, we get an answer of about, again, an answer that can be very, very close to 3 kilometers or 3,000 meters. It's very, very close. Now, it's very, very close to that number. What's interesting, and if you guys want to figure this out, because I tried figuring it out and it was a little bit confusing, is I was trying to look up doing this exact same thing with Messier 87. Do you know what Messier 87 is? You guys, have you ever heard of Messier 87? I bet you have. I guarantee you've heard of Messier 87.
No.
Messier 87 is the first image of a black hole ever taken. Does that ring a bell?
Yes. Yeah, I know the picture. I didn't know that it was called.
Yeah, I saw the picture. I didn't see.
Yeah, that's
like,
what I know.
Yeah,
It's one of those things where we've heard of it. We just, we don't know the name. So Messier 87 is supposedly supposed to be 2.4 billion times the mass of the sun. So it's basically 2.4 billion solar masses. So when I was just playing around with this, if you put that in the equation for Schwarzschild radius, the formula has worked so far. It works. But for some reason, so all you would do is you just simply take 2 times g times the mass of the sun times 2.4 billion, right? Because it's 2.4 billion times heavier than the sun. And divide that by c squared. Now, if you guys want to figure this out for me, that'd be great. I would much appreciate it. But when I do this, I get a value, and I tried it a couple of times, see maybe I made a mistake. I get a value about 7.1 times 10 to the 9 kilometers. But when I look up the Schwarzschild radius on Google, like the answer is very different than this one. It's at least twice as big, if not more. So if someone wants to look into that for me, that'd be great. But I don't know why it's different. Maybe one of the values is not right. But anyways, that's it. That's it. So do you guys have any questions about Kepler?
I have a question out of curiosity, just like Okay, sorry, I have a lot of questions. Okay, because you know how, so if something's heavier, its size as a black hole it would be bigger, right? That's why the sun is so big, because it's so heavy. Does that make any sense?
Yeah. There's a correlation between the size of the object and the Schwarzschild radius. Yes, for
Is it
sure.
directly, like if we what was I gonna say? If we double the size of the Earth, would its radius as a black hole also double? Like, is it proportional?
It is, because if you look at the equation,
Yeah.
R is proportional to the mass.
Yeah.
Yes, so if you double the mass, you should double the radius.
Cool.
Yes.
Cool. Fun. Okay, thanks. I was
Yeah.
just curious.
No problem. No problem. Any other questions, girls? Now, this has been recorded. So then what I'll do is I'll post this in Schoology. I'll tell you where it is. But otherwise, this is it. This is my 4th Zoom meeting today. Yeah, I know.
Busy, Sue.
Very busy. So I think that's it, girls. Why don't you enjoy the weekend, and then we'll talk again at some point over the next. Oh, I'll send you a message over the weekend about next steps. But that's it. Okay, girls.
Okay.
All right, ladies. We'll talk later. Enjoy the weekend.
Okay, Sue.
Bye. See ya.
Thank you.
Bye, girls.
Bye.